This video is part of the Rocketry Basics series. It explains the nomenclature of model rocket engines. The basic engine specifications are encoded into these part numbers to help you understand the characteristics of the engine. This video will help you learn how to select an engine for a specific application based on engine part number. This picture shows a variety of engine sizes. They range from the small mini or T engines that are 13 millimeters in diameter up to the large 29 millimeter engines that would be used in very large rockets. These are not the only sizes of engines available. There are actually engines smaller than this, but they are for very, very miniature rockets, so we don't normally consider those. And there are also engines much larger than these, which would be used in very high power rockets, which we also don't consider because they require a license to be able to use them. The engines that we're interested in are 13, 18, 24, and 29 millimeter size engines. Those dimensions refer to the diameter of the engine. Notice the smallest one on the left is a 13, then there's an 18, then there are two 24s. Notice one of them is longer than the other. And then there's also a 29 millimeter engine. The 29 millimeter engine in this case is a composite engine. The others in this picture are all black powder engines. There are some 24 millimeter engines that are also composite, but in general, the smaller sizes are black powder and the large size is composite. In this picture, the second engine from the left has a part number of C67. Let's talk about what C67 means. C67, there's three digits. A letter, which is a power classification. 6, which is an average thrust number, and 7, which is an ejection delay time number. All of those combined together form the part number for that design engine, and they also tell you what its characteristics are. Let's start with the power classification part of the part number. Power classifications are designated with letters. Each letter has twice the power of the preceding letter. It does not specify an exact power, but it specifies a 2-to-1 range. In other words, the C engine, our example, because we have a C67, has a power level of somewhere between 5.01 and 10 newton seconds. That's why it's classified as a C engine. Okay, that power level is measured in newton seconds, and obviously not all C engines are exactly the same. There's a range. If you want to find the exact power of the engine that you have, you'll have to go look it up in the manufacturer's data, or there's a very good website called thrustcurves.org, which is a website where you can look up test data for individual engines and find out what the actual power level is. By the way, the term power classification is technically not a measure of power, but a measure of impulse. What is impulse? Well, in general, impulse is defined as force multiplied by time. In the case of a rocket engine, it's the thrust multiplied by how long the thrust lasts. Okay, we measure impulse in newton seconds because thrust is measured in newtons and time is measured in seconds. For example, if we have an engine that produces 3 newtons of thrust that lasts for 0.83 seconds, 3 times 0.83 gives me an impulse of approximately 2.5 newton seconds. Such an engine would be classified as an A engine, and A is defined as somewhere between 1.26 and 2.5. The second digit of part number, which is always a number, is the average thrust produced by the engine. This is the thrust produced during the acceleration phase of flight. The value is given in units of newtons. For example, in our C67 engine, the average thrust will be 6 newtons. Again, keep in mind this is only an approximate value. To find the exact thrust for a specific engine, you'll need to refer to the manufacturer's data or go to thrustcurves.org. The third digit, which is also a number, is the delay from burnout until injection. In other words, it's how long the coasting phase of flight is. In our example of a C67, the ejection delay is 7 seconds. That means that the delay charge that starts burning when the fuel is exhausted burns for 7 seconds before the ejection charge goes off. Again, this is only an approximate value. To find the exact delay for any specific engine, you need to go to the manufacturer's data or thrustcurves.org. This is a summary of how the part numbers of engines from 1/4 A to F are encoded. Keep in mind that the values encoded in the part numbers are approximate values. To get exact values, you will need to look up the specific engine. This has been Rocketry Basics, Engine Nomenclature. The next video in this series will show an example of how to use engine part numbers to select an engine for a specific design. After watching this video, you should download and/or print a copy of the Engine Nomenclature Summary for future reference.